Hello, I'm Xiaojuan Hu. I'm here to introduce my poster. The topic of my poster is how to share and represent a large dataset of cation-coordinated conformers of 20 amino acid dipeptides. The first part is motivation. Mental catalytes are essential to life, and it's desirable to have fundamental and detailed theoretical understanding of the underlying peptide-cation interactions. However, force fields, which are typically being used in molecular dynamic simulations, suffer from large errors. The reasons might be that classical force fields neglect charge transfer and polarization effects, and their parametrization is often based on relatively small datasets. Here we present a large dataset from first principle study of amino acid dipeptides with and without divalent cations. And the study covers about 20,000 stationary points of the 78 systems. You can see the structures of the systems here. And we summarize the geometry information, total energy, electrodensity, electrostatic potential, and partial charges. For example, beta charge, Hirschfeld charge, and RISP charges. All this information can be used for force field parametrization. And the topic of this contribution is illustrating a way to make the data usable and accessible beyond just sharing a zip archive in order to make the data available for automated usage or to experts from other domains. And you can see the computational details here. The next part is dataset types and formats. Here we showed the file system tree of the dataset. And on the right side, you can see a figure of the workflow. And lower here is a figure about the number of conformers of each system. Making the data usable and accessible, possibly even to experts from other domains of science, is a challenge in itself. We can share the data with folders and files, but human intervention has to be involved. So is there a better way to share and represent the data? Here we give a brief introduction of ontology. An ontology defines a common vocabulary in a domain. It includes machine-interpretable definition of concepts in the domain and relations among them. Ontology is machine-readable, which in turn enables automatic access and querying of the data. And then we explained why would someone want to develop an ontology. Firstly, to share common understanding of the structure of information among people or software agents. This is one of the common goals of ontology. Secondly, to enable reuse of domain knowledge. People can easily reuse existing ontologies for their own ontology. Then to make domain assumptions explicit. And finally, to analyze domain knowledge. From this, new knowledge can be found. And then we discussed how we use ontological representation of the dataset. The first logical step is importing existing ontologies. Here we imported two ontologies, amino and amino acid ontologies. Details about these two ontologies can be found in these two links. And then we showed the hierarchy of ontologies. Firstly, there are two imported ontologies, and then the green ones are new created ontologies. In the future, we may consider to connect our ontologies with nomad ontology. Then we showed some contents of new created ontologies to give an overview about how these ontologies and the concepts connected with each other. And finally, here is the conclusion. We are using our data for the parametrization of proton force fields and sharing the dataset with our collaborators. And to make the data fair, we represent the amino acid metadata with ontologies and link to amino and amino acid ontology in order to ensure a common understanding of information. This furthermore enables individual scientists from other domains to make use of the data for their own research. Thank you for your attention.